Okay. Today we're going to talk about AVL trees. Programming assignment 2 is out still, and you should check Piazza for updates. Piazza has clarification on some of the parts of the programming assignment. So, like for example, how exactly you use level to determine who goes on the ordered structures or not. Today's plan is to do more AVL tree stuff like double rotate and remove. But before we do that, we have to warm up, of course. And our warm up is going to be actually kind of important. It's showing that AVL trees are short. So we want to show that they're not tall, they're short, they're not large depth. And in order to do that, we're going to look at the number of nodes, n of h, in the smallest AVL tree of height h. So this is the fewest nodes that you need to put into a tree in order to create a height h AVL tree. Now, maybe it's a little bit odd to think about a function of the number of nodes when we're actually trying to talk about height, but we'll see how that works out. And I'm going to, well, I don't know what the word is, encourage your intuition about the connection between the number of nodes in the smallest AVL tree and showing that all AVL trees are short by asking you the following two possible answer question. Do we want to show that n of h is big or small? If our goal is to show that AVL trees are short. So we want AVL trees to be short. We want to show that that's true. We want to show that the height is small. We want to show that height is less than some function of n. But the way we're going to approach the problem is by looking at the number of nodes in the number of nodes in the smallest AVL tree of a particular height. Do we want to show that that number of nodes is big, or do we want to show that that number of nodes is small? Two possibilities. Let's vote. Unless you have a question. You have a question?
Never mind.
Okay, good. So you understand the vote, right? Okay, big. We want to show it small. Good, good. Okay. Why big? Why would I want to show that n of h is big? What's the intuition for that? Yeah.
For small age, or for any age, we show that's a really big number. That means you can fit a lot of nodes in a very short tree, which is good, right?
Right. If we show that the number of nodes, the fewest number of nodes that we could put into a tree in order to get it to be height h, if we showed that that number was big, then the tree would have to be kind of fat, right? Bushy. Lots of nodes. Which means as a function of the number of nodes, the height would be smaller. So the bigger that we can show n of h to be, the better. If we show it to be really, really big, then h is going to be a very small function of that number of nodes that are in the tree. So that's the intuition. Now, there are a lot of people, or several people, that didn't have that intuition, but do you understand now what's going on? We want to show that there's lots of nodes that have to be put into a tree in order to get it to be height h. If you put 3 nodes into a tree, well, let's start off. Suppose I wanted to put the fewest number of nodes into a tree and have it be of height 0. How many nodes would I have to put in? That's n of 0. 1. N of 0 is equal to 1. Now, oh yeah, I forgot to circle. Big. How many nodes do we have to put into a tree in order to push the height up to 1? The fewest number of nodes. 2? 3? 2. You got a tree that looks like this. This is a valid AVL tree, and it has 2 nodes in it. It has height 1. So n of 1 is 2. Now, of course, there's another AVL tree that has height 1 that has 3 nodes in it, but all AVL trees of height 1 have to have at least 2 nodes in them. That's not saying very much because most trees that are height 1 have to have at least 2 nodes in it, but still, we want to show that there's a large number of nodes that have to be put into the tree before the height goes up. Height goes up to 3. And you could sort of think, what is the height 3 one going to look like? I don't know. What do you think? If I wanted to go up, I'm sorry, the height 2 one. If I wanted to go up to height 2, what would this thing look like? The smallest, fewest node tree with height 2. Okay, if I wanted to make something of height 2, I could do, okay, I add 1 there. But now I'm in trouble because the root node here has one child of height 1 and the other child is of height -1. And those two are out of balance by more than the allowed amount. They differ by more than 1. So I have to do something over here. I have to add another node in order to get a tree that's satisfying my balance condition and has height 2. And so, yeah, you're right. N of 2 is 4. Okay, well, that's interesting. What is N of H? What is the smallest number of nodes that you have to put into a AVL tree in order to push its height up to H? And I'm looking here for, what am I looking for? Pardon me? A recurrence. I'm looking for a recurrence. Exactly right. Yeah.
I mean, I don't know how to take this case into consideration, but it would be N of H minus 1 plus 2, I think, because you just add 1 node on each side on each subtree of the root, and then you keep the balance that way.
So you want to say, what's the value here?
N of H minus 1.
N of H minus 1
Plus 2.
Plus 2. Interesting. Yeah.
N from H minus 1 plus N of H minus 2.
And now we've got another vote for N of H minus 1 plus N of H minus 2.
Plus 1.
Oh, plus 1. Sorry. Any other possibilities? People want to have any other ideas? Yeah. N of H minus 1 plus H. Just make a chain down the other way. That's what you're thinking?
Yes.
Okay. Well, this little tree that I drew up here, this picture was supposed to be a bit of a hint. I mean, if I want the smallest number of nodes in a tree of height H, the tree has to be height H. What does that mean about the children? At least one of the children has to be of height H minus 1. Okay, so here's a child of height H minus 1. What about the other child? What constraints are on the other child? Yeah, there's the balance condition. There's a difference between the heights that has to be within 1. So I know that the other child has to be of height bigger than, or at least, H minus 2. And it turns out that the number of nodes to make something of height H minus 2 is less than the number of nodes to make something of height H minus 1. So I will choose, if I'm trying to make my AVL tree the smallest possible to have height H, I would choose my other child to be the smallest AVL tree of height H minus 2. So now you're looking pretty good. This guy right here, in fact, let me just erase this, and this, and this, and just write it here. So N of H minus 1 for the child that's got to be of height H minus 1, plus N of H minus 2 for the other child that has to have height at least h minus 2. So those are small trees. Plus I have to add 1 for the root. The root sits up at the top. Does everybody got this? It's sort of like structural recursion. Or structural, sort of? I'm trying to build a tree. I'm trying to construct a tree that has the fewest number of nodes in it. That's an AVL tree and has height h. And this is how I would do it. If there was a smaller way to do it, think about having a, if this was wrong, if there was a smaller way to do it, what would I do? Well, I'd use that as my recurrent, I'd use it in exactly this way to build something smaller for the next level. I mean, this is like, is it okay? Oh, no, I ain't trying to solve this thing. Oh, look, we already had a big talk about this. We just want to show that n of h is big, right? That's all we want to show. So we don't have to show exactly what n of h is. We just have to show that n of h is greater than something. So what is this greater than? Or greater than or equal to? What I'm doing here is simplification. Like I'm simplifying the recurrence because I don't want to solve the recurrence exactly. You guys are going to solve the recurrence exactly on your homework. But in class, I'm just going to solve a relaxed version of this recurrence. How would you like to relax this? What would be a nice recurrence to solve? It's certainly bigger than 2 times n of h minus 2. Is anybody feeling a little queasy, a little nervous right now? A little questionable? Like, what the heck? You're giving stuff away here. It's like I have n of h minus 1 plus n of h minus 2 plus 1. I've got lots of stuff on one side, and I'm just saying, I don't need to worry about that. I'm just going to take 2 times n of h minus 2, because that's, it's good enough for me. Yeah.
It's like when you're reducing it, like when you follow down the tree, right? N minus 1 will have a constant plus like its own recurrence. So like, why don't you just adding like 1 on each like recurrence? You know what I mean? So wouldn't it just be like less than, or n of h would be greater than the height because you just keep adding 1 each time you go down its recurrence.
Are you trying to argue that my approximation is nearly accurate?
Yes.
You are? How nice of you.
That's my question, though.
Oh, it was a question.
Yeah.
Okay. No, this is not exactly correct. This is strictly greater than. It's not exactly tight. I really am trying to introduce a notion here for you in your analysis of algorithms using recurrence relations that sometimes you don't care to get exactly perfect results. You just want to know asymptotically what's going to happen. Like we only want to know asymptotically the running time of AVL trees that have n nodes in them. And if we only want asymptotics, then we can satisfy ourselves with maybe simpler recurrence relations. We can maybe get that lower bound by using a simpler recurrence, and we save a little bit of time. That's what I'm introducing here. So for this thing, this simplified version where n of h is greater than 2 times n of h minus 2, what is the solution? So, do you want to try? Should I give you like a couple minutes and you can try to solve this guy? It's good practice considering there are going to be more recurrence relations showing up in this course. Let's do that. Maybe let's say 2 minutes and you can figure this one out. You got the substitution method, you got recursion trees, you got all these tools to use. Well, 2 tools. Try it. Everybody ready? Everybody need a little more time? Okay, what did people get? Same thing? I'm not done. I didn't finish. I was playing around up here. I didn't finish at all. What's the solution to this recurrence relation? I want something that says n of h is greater than some function of h. What function of h did you get? Anybody? Yeah.
I'm not sure, maybe 2 to the power of h divided by 2. And I'm not in English, sale. If you get the lower value.
Floor?
Yeah.
You want the floor or the ceiling? Ceiling is when you raise it up, or floor is when you bring it down.
Bring it down, not just the h or.
I think you want to go up. I mean, if you look at the base case, for example, it may indicate. Anyway, it doesn't matter. We'll just stick with h over 2. I think it's the ceiling of h over 2, but who cares, because the ceiling, 2 to the ceiling of h over 2 is bigger than 2 to the h over 2, so we're okay. Does everybody see why that happened? It's sort of like what's going on over here with these weird squiggly question marks. We do the substitution method for a number of times until we can get this part of our recurrence to look like a base case, which happens about after h over 2 steps. And so the question mark here is indicating h over 2, because h minus 2 times h over 2 is 0 or 1, depending on whether h is odd or even. And we'll get that h over 2 in the numerator. I mean, not the numerator, the exponent of the 2. So this is something like 2 to the h over 2 times constant, which is like, well, it's 2 if it was odd, and it's 1 if it was even. So let's just stick with h over 2. In general, it would be the ceiling of h over 2. Okay, so what? So I now have a solution, a bound on n of h, a lower bound on n of h, saying n of h has to be big. It has to be bigger. The number of nodes in an AVL tree of height h has to be at least 2 to the h minus 2 to the h over 2. So I can say, for example, by taking logs of both sides, that log of n of h is greater than h over 2. And that means that h is less than 2 times log of n of h. Right? And that's actually making me a little happy, because I really did want to show that h was small, that the height of an AVL tree is short. I wanted to show that it was short, but I wanted to show that it was short as a function of n, the number of nodes, and I've got this n of h over there. So if I give you an AVL tree with n nodes in it, and it has height h, what can you tell me about h? Tell me what you want to say. What do you want to say?
Less than 2 times the log of the number of nodes you have in the tree.
Yeah, you want to say h is less than 2 times log n. That's what you want to say. Why is that true? What's so special about n of h, the function n of h? Yeah.
Because n of h is the smallest number of nodes in the tree of height h. So any tree of height h must have the node like greater than or equal to n.
Yeah. This is true. This replacement works because every tree of height h has at least n of h nodes in it. So n, the number of nodes in our tree of height h, is greater than n of h. So this is for any AVL tree with height h and n nodes. Because we've shown this to be true, this inequality h is less than 2 times log of n of h, we've shown that to be true for the AVL tree with the smallest number of nodes in it that has height h. Yep.
Sorry, can you explain for when you said that n of h is in that expression was greater than 2n h minus 2? Like, what made you choose that? And
This right here?
get to our, yeah, like, how, like just that first step.
Well, I didn't originally do that. I originally had 1 plus 2 times n of h minus 2. I mean, I originally solved the recurrence for this, for n of h minus 1 plus n of h minus 2 plus 1. That's what I originally did. But then I decided that's good for you to do on your homework. And then I thought, well, okay, now we could easily do this if this recurrence was simpler. How much simpler could I make it without ruining the punchline? The punchline is really that the height is smaller than some constant times log n. And I knew, actually, I didn't have to go through this intermediate step because I knew what was going to happen. But I went through the intermediate step of saying, well, one approximation is that I could say n of h minus 1 and n of h minus 2, they're going to be close. So I'll just replace n of h minus 1 by n of h minus 2. And then I had this extra 1 sitting around, and then I got this series, which was 1 plus 2 plus 4 plus 8 plus 16. And then I was like, okay, forget that. I don't want to do this series again. They all know this series. So I decided I'd replace it by both of them, and throw away the 1. And it worked. And I sort of knew it would work. Right? Because I knew what the height was, and I knew that by throwing away the 1, I'm only losing basically log. But I have to tell you, this is not easy, right? This was like the first time I saw something like this, I remember feeling very, very uneasy. Like, where did that come from? I want to solve it exactly. I don't want to solve some sort of approximation. How do I know I haven't thrown away too much? How do I know I'm going to have to go back and do it again if I do it wrong? Why don't I just do it right from the start? Because it's faster, and you can check. This is easy. You guys know how to do this stuff like that now. At least as long as it's not really weird with this h minus 1, h minus 2 stuff. So this is an illustration of when you can get away with doing an approximation, and it actually gives you exactly what you want. It gives you asymptotically log n height for AVL trees. All AVL trees are height less than 2 times log n. You get it basically for free. I mean, it's really an easy recurrence. So, okay, now that I've used up all of our time, on to double rotation. Double rotations are what happen when you do an insertion like insert 6, and that causes an imbalance in this particular tree that is not solvable by a single rotation. You need to perform something else. And the something else that you do is you do 2 rotations. So in this case, we do a right rotation in the subtree below where the problem occurs. So this is, we inserted 6, and we noticed that that caused imbalance between the children of the node 4. And so we perform a double rotation by rotating first the pink nodes, and then we rotate the blue nodes. And that brings us back to having a tree which is balanced, and the height of that subtree is now restored to what it was before. That's 3. Okay? If you didn't get that, don't worry. Here it is with all those heights stuck onto it. the h's are heights. H plus 2 is the height of the root before we perform the double rotation. It's after we've performed an insertion. And by looking at this picture, I know that the insertion occurred in one of these two trees, here or here. Prior to the insertion, the height of the node B had to be what? What had this height, H, what did it have to be prior to the insertion? H minus 1, because it had to be an AVL tree, which means that these two nodes, C and the subtree W, had to be within height 1 of each other, which means this guy had to be height H. And the only way that's going to happen is if we reduce the taller one. And so I know the insertion occurred someplace inside of there. And what I'm doing now is rearranging. You can call it a double rotation or you can call it a manipulation of pointers. I'm rearranging the children so that instead of looking like an elbow, A, C, B, going like this, it's going like this. You put B in the middle. And then everything falls to the right spot according to the search tree property. All the things that are left are smaller, all the things that are right are larger than the node. And following that, you rearrange the tree. Is it okay? This is double rotate. 2 rotates. And what happens is the same as what happens in the single rotation case. The height of the new balanced tree is restored to the height of the original tree prior to the insertion. So this is the height is restored to its pre-insertion value. Have any questions about this? Yeah.
I don't see where the height is being restored. Like in what?
Oh, so what's happened here is I'm taking a tree that was after the insertion that was of height h plus 2.
So that's after you insert.
This is after insertion. And then I perform the double rotate, and it actually decreases the height of the root by 1, which brings the tree back to what it was height-wise before the insertion. Because the insertion is the thing that caused here. Let's suppose the insertion was in the tree subtree X. That node caused this subtree to have height h minus 1, which caused its parent B to have height h, which caused its parent C to have height h plus 1, which caused its parent A to have height h plus 2. And that chain we're kind of twisting in this rotation to bring things into more equal balance. And that's what's happening. And after that, the heights are restored to what they were before, or the height of that subtree is restored.
We're assuming we're like inserting to the bottom basically, and that's causing the imbalance, which forces the rotate.
Oh yeah, so this is a good question. When I insert into an AVL tree, the insertion that I perform is just like an insertion into a regular binary search tree. It goes all the way to the bottom and puts it in as a new leaf. You could get fancy and try to insert it in the middle, but that's not what we do. Yep.
How would the tree look like if it's just doing one rotation?
You mean if I just did one of the two?
Yeah.
Well, it would pull like here. This is the rotate right. Oh, I can show you. It's like this. This is the first rotation that's done, is to this subtree of where the problem is. And it creates this tree, which doesn't look balanced at all, right? No, it's not. But that's because it's only the first step of the double rotation. The second step is that part, and it restores the balance, brings it back up. I mean, I encourage you to think about it in either way that makes you happy. you can either think about it as being two rotations, like in this picture, where you see a pink rotation and you see a blue rotation. Or you can think about it like this picture, where it's just a reassignment of pointers. All I'm doing is saying, in this tree, I'm shuffling around the subtrees W, X, Y, and Z, so they are basically in the same order, but the parents and grandparent are now organized differently. There's A, B, and C. B is now the root, as opposed to A. Yep.
Is there any motivation for why we should be able to look at a tree and determine where the insert happened? Because anytime we're modifying a tree, don't we know where the change already happened?
Is there any motivation? No, there's no motivation for you doing that. I just know that it happens to be in there because of the heights. So this was just a vehicle for me to describe what happened to the heights when the insertion was performed. So if I give you heights in a new AVL tree, you should be able to figure out where the insertion occurred if it's not in balance. Okay, everybody good? Here's the code for doing insert. Find the location for the new key, just like you normally do. You follow the left and right children depending on the value of your key compared to the parent, the root value. And you add a new leaf with the new key at the bottom of the tree. And then either you follow parent pointers or you return from your recursion. You go up the tree from the new leaf, searching for imbalance. And as well, you are updating heights as you go. Now, as you go up, you're checking for imbalance, you're updating the heights. You get to a certain point, you might find that you have an unbalanced ancestor of the leaf that you inserted. So you're going up, you get to a node, it's this node, the black dot is out of balance. And I'm just showing schematically what the tree might look like. And let me tell you that the insertion occurred in that subtree. That little triangle down there, there's a 2 R's in occurred, in the triangle subtree. So I got that insertion. If it was the case that that insertion happened in the left child of the left child of the node where the imbalance is, then I perform a single rotate right. If, on the other hand, it was the right child of the right child where the insertion occurred from the node that's out of balance, I would perform rotate left. If it's an elbow or another elbow, then I either do rotate left right or rotate right left, depending on the path that I take or I have taken back up from the insertion to get to this node of imbalance. And that fixes it. Don't worry, we're going to do some examples. But do you understand the code? The codes go down and then start updating heights, looking for imbalance. If you find imbalance, then you check where did it come from, where was the insertion coming from, and depending on where it came from, there's only 4 cases. You perform a single rotation left, single rotation right, double rotation, double rotation. Yep.
You say that you can go off the tree from the new leaf. Does that mean you also have like the child knows about it, like there's a pointer to the parent?
If you'd like to do that, you can.
Or like, but in the case that you only point to your children, does that mean like, when you're finding its location, you have to add it at that time? Provided we don't have ancestral pointers, only descendants.
You have to add it at the time you got to the node that you're adding it to.
Yeah.
Yeah, but that's true no matter what. Even if you had parent pointers, you have to get to that node in order to add a pointer to that new leaf child. The question is, when you get there, can you just sort of like iteratively back up? If you had an iterative solution, then you could use parent pointers. Or you could use a stack to keep track of where you came from, which is essentially what recursion is doing for you. for free. No. Okay, let's do an example. Okay, let's insert 3 into this tree. Here we go. So we take 3 as the key. We compare 3 against 10. It's smaller. We go to the left. You guys know how to do binary tree insertion, right? Okay. Compare it against 5. It's smaller. You go to the left. Compare it against 2. It's larger. You go to the right. It gets added here. Now we start crawling back up out of the recursion, assigning the new height values to these nodes if necessary. The leaf has height 0. We go up to the parent. The parent says, oh, I've got a child of height 0. My height has to be 1 plus my tallest child. So I have height 1. I go and I look at my parent. Oh, I got to check. Is this a out of balance node? Node number 2, is it out of balance? No, it's okay. Because one child is -1 height and the other one is height 0. So they're within 1 of each other. So -1 is nil over there. So I go up to the node 5. I update its height. And now I check its children. 1 versus 0. I'm okay. So then I go back up to the root of the tree and I check, calculate its height, which is 1 plus the height of its 2 children. That's still 3. I don't have to change anything. In fact, I could stop at this point. If there was more tree to go to, I don't have to go anymore because no more heights are going to change. Could abandon the thing right there. But this is I can abandon because that's the end of the tree. Okay, so now, great. That was easy. That's the no imbalance case. Here's the case for rotate right. So now insert 33. 33 goes this way, this way, this way. 33 goes right there. It has height 0. Is 30... Oh, yeah, we got to correct this. That's not right. Now 30 is height 1. Is the node 30 out of balance? No, we're still good. So we back up to 20. 20 has height 1, not anymore, it doesn't. It has height 2. Is it out of balance? No, it's not out of balance. So we back up to node 15. 15 is now of height 3. Is 15 out of balance? Yeah, it's in trouble. So this is out of balance node. We have the 2 edges that are coming. The last 2 edges that we used to come up were both right edges, right child, right child. So now we know we're in the RR case, and we will perform a rotate left. We're going to rotate that way. Here we go. Rotate left. Yay! You've seen those before. Not hard. That's the code. Now, there are 3 pointers that change from going from this picture to this picture. Picture A to picture B. There's 3. One of them is this pointer. One of them is this pointer. And one of them is this pointer. Those are the 3 pointers that change. There are 4 equal signs here. So one of them is not a change of the pointer. Can you tell me, that's number 1, that's number 2, and that's number 3. What is the piece of this code that changes pointer number 1? What line of code changes pointer number 1? You can see the last one. Oh, very interesting. That A equals B is A is a reference parameter. And so that A equals B, that innocent-looking assignment operator, is actually changing the pointer that has been handed by whoever called this function. It's changing that pointer into something new and different. It's changing it into B. So now A points to B. It no longer points to A. This is kind of cool. How about number 2? This is the right child of A. Yeah, there's only one assignment to the right child of A. It's happening right there. And then what about number 3? Right below number 2. So those are the 3 lines that are actually modifying the pointers that are in the data structure. Those 3 lines modify the structure. This line, the 4th line with an equality, is simply like a temporary variable. It's giving you a way to grab a handle onto the right pointer of A, because you know later on you're going to have to modify the original reference pointer A. You're going to have to modify it to be that pointer B. You have to stash it away because you're killing the right pointer of A on line 2. Okay, everybody good? Pretty straightforward. This is like pointer manipulation, like 201. Yeah.
For update height, does that mean that we have to like traverse the whole tree so we cover the height?
Ah, update height. How does update height work? What does update height do? Oh, you already know the answer. Okay.
Okay. I was thinking like, I feel like that implies it's gonna traverse and like go through every subtree. And I was like thinking like, why would that be necessary? Like, why can't just like add 1 and subtract 1 from the heights? But then like, what if like y is really big? Or
Do you remember what one of these nodes looks like? What are the fields in one of these nodes? This is exactly why I keep height inside of that structure. Height is actually set for the children accurately before I come to the parent. So in order to update the height of A, I just need to check the heights of the children, which is a field that's within the children. So it's a constant amount of work to check those. Take the max and add 1. So that's giving me, these are order 1 operations. So this rotate left code, how much time does it take? Same, order 1. The whole thing is constant time. It's based. The children are there. The whole insert code. Insert takes log n time because it has to perform this potential update at every level. Potential rotate. I only has to rotate once. Is it good? We've got to get to the next thing. It's very exciting. Okay, let's insert 18. Okay, this is like you go this way because it's 18. You go this way because it's 18. You go this way, 18 is less than 20. But 18 is larger than 17, so it goes down here. It's new. It has a new height of 0, which means that its parent, which used to have height 0, is now bumped up to height 1. Its grandparent is now bumped up to height 2. And its great-grandparent, oh, by the way, are we checking balance? Have you been checking? I haven't been. Everything's okay? And this guy changes to 3, and now we keep going. No, you scream, stop. We have a child of height 0 and another child of height 2. The difference between them is 2. That's too much. So this node, again, node number 15, is problematic. It's out of balance. And we need to fix it. And how do we do that? Well, in this case, the insertion occurred not in a chain that was straight, like left-left or right-right. It occurred in the right-left subtree. That means I have to perform a double rotate. Rotate right-left. And that's what I do. I rotate first down here. So I go back down into the tree. I perform a rotate down here. And then I perform another rotate here to get to the final double rotated tree. Yes?
Does that mean just walk through it again? It's really confusing because when you counterintuitively rotating left and right is just doing the opposite thing.
No, but you're doing it at different points. So you're doing the rotate right down here at the node 20, and you're doing the rotate left up here at the node 15. So you're doing it at different spots. You're not undoing what you just did. Okay, we've got like 1 minute to do this, right? Or 2 minutes. Do you think we can do double rotate code? Because the next slide is the code slide. Well, if it doesn't show up, that's easy.
Just dislikes you today.
There we go.
There you go.
That's the code. It's like 2 lines of code. Isn't it cool? You do a rotate right down here at this node, and then you do a rotate left up here at this node. It's just lovely. It makes reference parameters, makes me happy.
So that means the initial rotation will be done the first parent after the imbalance, and the second rotation is done at the point of imbalance.
Correct. If you know this pointer right here, the pointer that goes from A to C, is modified by the first rotate right code. It's modified so that it now points to B. It no longer points. So the change in this pointer happens in this call because it's passed by reference. And then the A is updated because it's passed by reference as well. Okay, great. I have one more thing to tell you, which will take 1 minute. It's about delete or remove. When I remove from a tree, for example, if I remove 1 from this tree, you'll notice that I cause imbalance. This tree all of a sudden becomes imbalanced because this child now no longer exists. It's a -1. And I have a sibling that's of height 1. And so I cause imbalance. And I have to restore that imbalance. But when I restore the imbalance, I decrease the height of this node to 1 from what it was before, which was 2. And now I cause more imbalance. So I decrease this, that decreases this by 3. Now I've got another imbalance. So this is a situation where a single rotation doesn't fix everything. You perform these kind of rotations in order to restore balance, but they drop the height of the tree and cause imbalance at the parent level. So delete will cause multiple rotations. But again, rotations are cheap. They only cost constant amount of time, and you have to do at most log n of them. So the running time of delete is also order log n. It's just more complicated. Okay, by the way, this is called a Fibonacci tree. That's true. It's called a Fibonacci tree. It's cool.
Why?
Why not? Okay, I will see you on Monday.